Dr. Karthik, working as a research engineer in this office for the past 1.5 years. So I extend my warm welcome to each and every one of you for today's guest session on precision manufacturing as part of Excellent Engineering Series as initiative of TANCAM. So the main purpose of this program is to upskill the internal quality of our team so that whenever we are doing external projects for the clients, we don't rely on too much on the online data. We will have a clear understanding of what we are going to do. Okay, of course, we are all well equipped with whatever we are going to perform and whatever we are going to do in our software, but enriching our knowledge is also very much important. So Excellence Engine Series as initiative taken by TANCAM is one of the unique ones of the 3 Center of Excellences, where we will be inviting eminent professors from renowned institutes for delivering lectures. So we are truly honored today to have such esteemed personalities among us this evening. Before we begin, I would like to take a moment to acknowledge and introduce the distinguished guest who has joined us today. So it is my great honor and privilege to welcome you all to today's guest talk session. We are fortunate to have Professor Dr. P. Vamsi Krishna sir, a distinguished academician and researcher who currently serves as professor in the Department of Mechanical Engineering at the National Institute of Technology, Warangal, India. Dr. Vamsi Krishna sir has over 21 years of rich experience in teaching and research. His areas of expertise include application of solid lubricants and eco-friendly nano-cutting fluids in machining, vibration-assisted machining, in which I pursued my PhD, modeling and simulation of manufacturing process, and composite materials. He has successfully guided 5 PhD scholars and 5 more currently pursuing their doctoral degree under his supervision. He has also mentored 35 postgraduate students and 19 undergraduate students, contributing significantly to academic development at various levels. Dr. P. Vamsi Krishna sir has completed 500 research projects worth rupees 2 crores, funded from various institutions like Department of Science and Technology, Government of India, University Grants Commission, and various other renowned institutes, with one more ongoing and has prolific contributions to the research community with over 130 publications in reputed journals and conferences. He authored one textbook and also co-authored 3 textbooks and 3 book chapters and edited 3 books, and he holds one patent on drilling machine. He is an editorial member for 10 international journals and also delivered 35 invited guest lectures. So he organized different seminars and workshops in his tenure in National Institute of Technology and many international conferences, and he is named as one of the top 2% most influential scientists in 2022 Stanford University list. He is one of the outstanding reviewer award by Tribology International Journal, which is a high-profile journal in the science community in 2017, and he also earned Best Reviewer Award from Transaction of Indian Institute of Metals in 2020. Today, he is sharing his insights on a relevant and evolving topic, precision manufacturing, to all of us, an area that plays a pivotal role in modern engineering, quality control, high-performance product development. So we are truly honored to have him with us. Please join me in warmly welcoming Dr. P. Vamsi Krishna sir for this event. Thank you. So with this, I quickly conclude, and at the same time, I welcome our Tancam mentor, Sauri Rajan sir, who is one of the key initiators for this kind of engineering activity. So with this, let us start the presentation, and then we'll have a quick facilitation of our guest, followed up by vote of thanks, and you can have a interaction session with him regarding your your doubts in your future aspects or the subject, whatever it can be. Okay, so thank you.
Yeah. The most important thing is more than he has read a lot of laureates and other things. Okay, and Professor, the most important thing for me, you have produced such a guy. Okay, that is the proudest thing for a teacher. Okay. And I want to inform you, and we are very happy. And he's interacting with more than the things. He's interacting with all the people very kindly and politely and personally. Okay, that's very important, and is knowledgeable as well as a lot of good manners and other things. We are very, very, very thankful for your mentoring for him to become something like this. Thank you very much for that. And so let's take his knowledge from him directly. Please carry on.
Okay. Yes, sir. You can write about it. One second, sir. I'll give you the Bluetooth. Please connect it, Dinesh. Check whether it is connected or not.
So wait. place the volume. Check SAR is visible and that presentation should be visible. Okay. If needed, you push it a little back.
Okay. Sir will be standing there.
Okay. Fine.
And right.
SAR will be coming this way.
Okay.
This is for happy. Yeah. Fine. Okay.
Okay, good evening everyone. So today I just want to give a small introduction about the precision manufacturing. I think all of you know, maybe in your BTech level or MTech level, we use tolerances, right? In the manufacturing, we give tolerance, right? What is the purpose of tolerance? You are doing so many drawings, right? Maybe models. So in the manufacturing industry, if you want to manufacture any component, we cannot manufacture to the exact size, right? So we give tolerance on each part. Why we are giving the tolerance? Because we are not able to manufacture the component to the exact size. Okay? Because so many things. Even though if I say maybe for example the height of this bottle is maybe 15 centimeters. How can you ensure this? I can say the height of this bottle is 15 centimeters. How can you ensure this? How can you test this?
Using measuring tools.
So you can use something, maybe scale or tape or something, right? So because of this irregular shape, we have to measure indirectly, like measuring our height. So we can mark on the wall and you can stand and we can measure the height, right? Similarly, we can able to measure the height of this bottle also. But is it correct? It may not be accurate, right? So while marking itself, we are doing some mistakes, or maybe there is error in the whatever tape you are using, or there may be parallax error while taking the reading. Like that, there are so many reasons in the measuring systems, or measurement units, or maybe measuring instruments, etc. So that's why normally we cannot manufacture any component to the exact size and shape. 100% accuracy is not possible, right? So first we need to understand the accuracy and precision in the manufacturing. Of course, we use this word very frequently, but both are not same, right? So what is accuracy? This is accurate, right? But and also it is precise. Or I'll start with here. So this is not accurate, not precise. So as per this one, we want the target here. So as per this one, we want target here, right? So we want target here, but the target is hitting at different places. So what is accuracy? If you are able to reach the goal with less error, then we can say accurate. Then what is precision?
The more number of times we need to get the same point.
Not more number of times. Whatever number of times you are repeating, if you reach the same accuracy, then we can say the precise. Right? So if you see, all the four are different distance from the center. So these are not accurate because it is not in the inside circle, and also even all the four is not at the same distance or at same point. So this is not accurate, not precise. But if you see this one, this is accurate because all the four are at the same distance from the center, but it is not precise. Why? Because every time it is changing its place. Okay, and if you see this is precise, so whatever 4 times or 10 times you are doing, you are getting the target at the same point, but it is not accurate. And this one indicates both accuracy and precise. Okay, that is, for example, uh, we are preparing for something, maybe running race, or you are writing the test, maybe some JEE or something entrance test. There are two things. Getting maximum score is important. At the same time, every time getting the maximum score is also important. Suppose you are doing B.Tech or M.Tech or something, right? If you are scoring in one subject 90 marks, in one subject 40 marks, then there is no use. So if you are getting in all the subject 90 marks, this is very good. Or at least all the subject around 70%, that is also good. Or if you are getting one subject 45 marks, one subject 90 marks means, so you are not good in all the subjects, right? That is what we understand. So similarly here, we see accuracy and precision. So in the manufacturing, we want both accuracy and precision. Okay, that means suppose one time you are able to reach the goal within time, but next time you are not reaching within time, then there is no use. So if you developed a software or if you developed a machine, etc., anything, so every time over the repetitive times you are able to achieve the minimum cost or maximum production or high quality product, then only we can say it is precise, right? So both accuracy and precision are important in the manufacturing. Even though if you are accurate also, it is not sufficient, or if you are precise also, it is not sufficient. And also many times we use these two words simultaneously, but it should be very clear, right?
Right. So now we are coming to this. I think all of you know the tolerances. That's what we are discussing. So if you want to manufacture any component, normally we define a tolerance. That is, for example, if I want to manufacture a
So if you want to manufacture one shaft, right? So normally what we can do, we define the diameter is equal to maybe 20 mm or plus or minus. So we take the dimension as 20 plus or minus 0.1 mm, right? That means actually the basic size required is 20 mm, but we cannot manufacture exactly to the 20 mm. So we have to give some tolerance, right? This is what we see in our daily life also. Your office is at 9:30, but are we exactly coming at 9:30? Some people may come 9:20 or 9:25, or some people may come 9:35. Even everyone come at 9:30 also, you cannot enter into the door, right? That means we have to give tolerance on both the sides. Sometimes it is not possible. So, if you are giving tolerance on only one side, we can call it as unilateral tolerance. Or if you are giving tolerance on both the sides, then we can call it as a bilateral tolerance. I think these are the basic things all of you know, right? And also, when you are making a assembly, right? So single component we cannot use. That is very rare cases. Mostly whatever we are using is assemblies, right? Suppose you want to use this bottle, we can make the cap as well as the bottle, right? So if these two are assembled, then only the functionality is sustained. Or if you take a pen, again it contains so many number of components, right? A refill, right? And again refill contains ink, tip, etc. So each one is perfectly manufactured, then only we get the functionality. Suppose you take this one, you take this refill. If the length of the refill is slightly increased, then what is the drawback?
Not fitting to this.
So it will not move. At the end, it is obstructing. At the same time, if the length of the refill is less than the required one, then while writing, it is moving inside. So both the cases, the functionality is deviating. Okay. So like that, normally in all assemblies, if you want good functionality, we have to follow these tolerances, right? And also the type of fits. So normally we have three major types of fits: interference fit, clearance fit, and transition fit. So in the clearance fit, whatever you take, that is the lower limit of the shaft and higher limit of the shaft. So normally we can say this is lower limit of the shaft and this is higher limit of the shaft. So this one is the tolerance on the shaft. And similarly, here you take this is the whole dimension. This is higher limit and this is lower limit. So this is the tolerance. So if you see, the lower limit of the hole is always greater than the higher limit of the shaft. That means if you manufacture a shaft, whatever the value, you are going to get a clearance. And similarly, if you see here, always, even the lower limit of the shaft is bigger than the higher limit of the hole. So always you are going to get the interference. So in these two cases, no issue, right? Because already always this limit is bigger than this limit, and here this limit is or this limit is bigger than this limit. But if you see this one, the transition field, for example, if the actual dimension of the shaft is here and the actual dimension of the hole is here, then you are going to get clearance, right? But for example, if the actual dimension of the shaft is here and actual dimension of the hole is here, then you are going to get an interference. That is why we can say transition fit. Okay. So in the manufacturing, depends on the functionality, depends on the dimensions, or maybe depends on our constraints. Suppose you are given the limits like this in the transition fit. Okay. So you are manufacturing two components like this in the transition fit. Then, but even though if I am manufacturing like this, but I want always a clearance. You got my point? Here, there is a possibility of clearance or interference. I am following this system. I am following these limits. But still, after manufacturing a lot of shafts and lot of holes, in the assembly, I want to maintain always a clearance. How can I get it?
Bilateral intolerance.
Pardon?
Unilateral tolerances. By
Unilateral.
using unilateral tolerance,
No, I'm giving the dimensions like this only, right? But I'm not manufacturing single shaft and single hole. No one will manufacture. So we are manufacturing shafts continuously, and we are manufacturing the holes continuously. But while doing assembly, I want clearance. How can you get it?
machining.
No, I am not going to do anything. Only I use this only.
upon the assembly, we can choose the types of fit. So clearance fit, depending upon one type of assembly. Transition fit depending upon another type of assembly. For example, the pen and tap here. First, it's a colon stop basis method.
Yes.
This is called as transition.
Yeah, that is what my question. Actually, we are following this system based on the component manufacturing, based on the maybe material constraint or dimensional constraint or whatever. But we are manufacturing in the transition fit individually the shafts and holes. But while assembling, depends on the functionality. Sometimes I want clearance in one product, but in one product I want interference. How can I achieve that one? This is so simple. I'll give you a small example. So, for example, you have 100 people, right? 100 people from one college and another 100 people from other college. All 100 people are cricket players, okay? But all these 100 people, maybe few are batsmen, few are bowlers, or few are all-rounders or fielders, like that. There will be a combination, right? Now, other side also same, okay? So if I want a team, right, which are very strong on the batting side, you can see sometimes depends on the ground, depends on the opposing team. We can change the mixing of the players, right? Sometimes we use fifth bowler, sometimes we use fifth batsman, like that. Why? So we know already, depends on the ground condition, that may be a batting pitch. So we can use extra batsman. Or depends on the bowling pitch, we can use extra bowler. Or sometimes we use fast bowlers, sometimes we use slow bowlers, like that. Am I right? That means from the available pool, you are selecting. Players are same, but depends on today's match, you are selecting. Am I right? Even in our daily life also, we can do so many things, right? So today you are coming to office, or maybe you are going to shopping. You have a list of things. You want to purchase 10 items, right? But you don't have that much money. Then what we can do? So we can prioritize, right? What is first, what is next? So among that we select few things and you can do the shopping, right? So similarly, here what we can do is, next slide. Right. So similarly, we use the selective assembly. Okay. So that is, for example, if you are manufacturing 100 shafts and 100 holes, right? And I want to mix these two to get the 100 assemblies. But among these 100 shafts, for example, we take a shaft like this, right? And the tolerance zone is this one, for example. Then we don't know how many are at the lower limit and how many are at the higher limit and how many are at the exact dimension, like that. Similarly on the hole also. Now what I can do is I divide these 100 holes into 5 groups and I divide the 100 shafts into 5 groups. That is, groups means nothing but the same tolerance zone I divide into 5 parts. Okay, so I can assume the tolerance zone is totally like this. Okay, so So now I can divide this total tolerance zone into 5 different parts, and after measuring with go gauge or no go gauge or whatever, then whatever components in this region I can make it to group 1, and here I can make to group 2, group 3, group 4 and group 5. Similarly, these are the shafts. Similarly, holes also I can make into 5 groups. Now I cannot assemble randomly. Okay, actually all these 100 holes and all these 100 shafts are within the limits only. All are accurate only. All are qualified for the assembly. But still I am not randomly assembling. So I can make the holes also into 5 groups. Then I will take the shafts in the group 1 and shafts in the holes in the group 1, and I can assemble only group 1 to group 1. Are you understanding? So for example, here you take the lower limit is for example 20.0 mm, and the higher limit is maybe 21.0. Then this may become 20.02, 20.04, 20.06, 20.08 and 21, like that, or 20.2, 20.4, 20.6, 20.8, 21, right? And similarly the whole dimension also same. So if I assemble the shafts in this group and the holes in that group with the same tolerance zone, but we are able to get the assembly with very less clearance or less interference. So we are not changing the tolerance on the shaft or tolerance on the hole. So we are not increasing the cost, we are not changing the manufacturing process, we are not changing the material. Only thing is, before assembly, we are just making the groups and we are separating it and assemble group 1 to 1. Okay. So like this, this is one technique, maybe grouping of the components based on their tolerance zones, so that we can able to increase the accuracy of the assembly or functionality of the component or product just by making the groups in the tolerance this one. So how many groups we can do, that is up to you. Depends on the tolerance zone. Maybe you can make into only 2 groups or 3 groups or 4 groups or 5. But one condition here is the number of groups you are doing in the shafts and number of groups you are doing in the hole should be same. Then only this tolerance zone is divided into 4 parts or 5 parts, and the same tolerance zone on the hole also divided into 4 parts or 5 parts. So like that, without changing the manufacturing process, without changing the material, or without changing the assembly process, without changing anything, we are able to increase the accuracy just by making a group and assembling particular group to particular group. So this is one of the concept maybe we can follow in the precision manufacturing to improve the accuracy of the product as well as functionality of any of the product, right? Is it clear? Any doubts? Previous slide.
Cancel.
Previous slide. No, alright. So I think that's it. I think this one all of you know. Maybe you should know, if you completed BTech means you should know, right? So this is actually the fundamental deviations we can see on the holes and shafts, right? So we have normally we use 18 grades of tolerances and 25 fundamental deviations, right? So this one is A to ZC. This is the fundamental deviation we indicate on the poles, and these are the fundamental deviation we indicate on the shafts. That is, for example, we write like this, maybe 20. So we can write maybe 20 H7 by F8. That means 20 indicates the basic size, and capital H indicates fundamental deviation on the hole. H means not hole. Any letter which we are using like this, but capital letter indicates the fundamental deviation on the hole, and the small letter indicates the fundamental deviation on the shaft, and this number corresponding to this capital letter indicates tolerance on the hole, and this one indicates tolerance on the shaft, right? So that means H is 7. So this is a H. So this is the fundamental deviation on the hole, or maybe you can take the other thing like this. Yeah, it's okay. And F is this one. So this is 20. Basic size is 20, and if you see here, the fundamental deviation is coinciding with the 0 line. Okay, that means for this hole, the lower limit is 20.0. This is the lower limit, and higher limit is equal to 20.0 plus the tolerance corresponding to the grade IT 7. I think all of you know how to calculate the tolerance, right? So this is a lower limit and this is the higher limit. And similarly, this is for hole. And similarly for the shaft, if you take the basic size is 20 and the tolerance is this one. So this becomes a higher limit of the shaft, and this becomes a lower limit of the shaft. So now the higher limit of the shaft is equal to basic size 20 minus this gap, that is the fundamental deviation. Okay, and the lower limit is equal to, again, this is the tolerance. Okay, so like this, normally in a assembly, if you know the basic size and fundamental deviation and the tolerance, we calculate all the limits on the holes and the shafts, right? Okay. But here, one more thing is there. So here one more thing is there. Again, in the transition bit, there is a possibility of either interference or clearance, right? For example, you take this is the hole. So the lower limit of the hole is this one, and higher limit of the hole is this one. And the lower limit of the shaft is this one, and the higher limit of the shaft is this one. Okay. Now, after manufacturing in this size, if you take this size 40H7 by M6, for that this is the diagram. Okay. So this is nothing but 40.0 lower limit of the hole, and this is nothing but 40 mm plus 25 micrometers. Okay, and this is the lower limit of the shaft, that is 40 plus 9 micrometers, and this is a higher limit. So after manufacturing, what is the actual size of the hole? We don't know. It may be here, or 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 it may be here. We don't know. Okay. And similarly, after manufacturing of the shaft also, it will be somewhere, right? We don't know. So then, if you follow this one, and if you manufacture a hole and shaft, after assembly, what you are going to get? Or clearance or interference? How can you say?
We're making into groups.
Forget about that one. That groups is another concept. To improve the accuracy, we can do the groups, and within the group we make the assembly. Depends on whatever clearance you want or whatever interference. Now we don't have groups. Only we manufactured one hole and one shaft. Now I am assembling. So what is the probability of getting clearance or interference? How can you say? Because the definition of the transition bit is either clearance or interference. Then how can you say?
50-50.
No? So here we need to understand one more thing. So you take this tolerance zone. So this is the center line for this tolerance zone. Okay. So this is the mean value for this tolerance zone. And similarly, if you take this tolerance zone, you take the mean value of this tolerance zone. Now you consider only mean values. So if you consider the mean values, the mean value of the hole is lesser than the mean value of the shaft, right?
Yes.
And also always the manufacturing, this follows the normal distribution curve. That means if you manufacture 100 components, 100 holes and 100 shafts, the actual size of the hole and actual size of the shaft follow this normal distribution. That means if you find out standard deviation for this one, and that 2 sigma components are within this range, and another sigma components are within this range, and very few components are within this range. So that means most of the components are near to this mean value, at least some 68.26%. So if you check like this, that is, even though the basic size is here 40.0, and we have lower limit and higher limit, and here also we have lower limit and higher limit, but again you take the mean value and then compare. So from the mean value, what we understand here is the whole size is less than the shaft size. Okay, so what is happening is here the probability of getting interference is more, but how much more? So here the probability of getting interference is more than 50%. Okay, for example, if this mean value is greater than the mean value of this one, then the probability of getting clearance is more than 50%. All of it clear? So from this one we understand the most of the cases either you are getting clearance or interference. And also by calculating this standard deviation value and by finding this standard deviation 1 sigma, 2 sigma, 3 sigma, etc. Right? We can able to calculate what is this difference. This is 17 minus 12.5. That is 4.5. So if you calculate this standard deviation and you can take the equivalent standard deviation. Actually here interference is there and that also it may come somewhere here based on the percentage of area covered under this 6 sigma limits. So all this is interference and this is clearance. So the probability of getting interference here is maybe around 74% or 77% and getting clearance is only 20% or 22%. Okay, I'm not going into the calculations, but like this we can able to exactly find out what is the probability of getting the clearance and the interference. Okay, see I am not touching the basic things of like what is tolerance, what is fundamental deviation, etc. because all of you know these things. So these are the two important points normally we don't study in the BTech level, right? That is without changing the tolerance, without changing the manufacturing process and material condition, etc. how to improve the accuracy, that is one point. And also when we have a transition fit type of manufacturing, what is the probability of getting either clearance or interference, right? So you want more clearance, then you keep this one below this, keep this one. Like that you select this. Like that you select these fundamental deviations. Okay. So these are the two important concepts maybe we can follow to get the more accuracy and precision in any of the manufacturing process. Of course, for these things we have exact calculation also. That is how much exact percentage we can get, or maybe how many groups we have to do, and by making the groups into how much accuracy we can able to improve, etc. But I am not going into deep dive. Just try to understand the concept, right? Right. I think you heard this one, GD&T. So maybe in the BTech level, we don't discuss this one, right? So that is what previously also we are talking about. For example, if you have the hole and the shaft. For example, we take this is the shaft and this is the hole. Normally, we define diameter of the shaft, diameter of the hole, and also we give tolerance on the shaft and tolerance on the hole, right? But sometimes I think most of you observed we use racks in the table, right? So those racks are there. Sometimes the rack will not go freely. Why?
This is due to moisture can be lost.
Pardon? Even though you manufacture that rack, outside one and the box to the exact dimension, but it will not go freely
Due to the
Roughness.
condition.
Roughness.
Pardon?
Roughness of the
Roughness. Okay. Any other reason?
because of interference. Because of interference.
Interference. No. Already we are taking care of that fit type of fit.
Because of surface finish. Surface finish is not
See, this bottle is there. I am fixing the cap. Sometimes it will go freely, right?
Due to material.
See, sometimes it will go freely, but sometimes it will not go freely. All of you experience this one. Why? What you can do then? Huh?
Wrong sometime temperature. Fixing it properly.
Properly means
So positions. Environmental.
the same. If I am keeping cap like this, you can see all of you observe, and I rotate, it will not going properly. Sometimes, but sometimes it will go. Now it is going properly. There is a small difference. Maybe
How
this
you are
cap is
handling?
very small. That's why you are not able to observe.
The handling. Waiting the guidelines.
You can say technically.
Alignment.
Right, alignment. Right? So, the same thing. We use so many times. Maybe this type of things you want to fix into the system. Sometimes it will not go properly. Then you can remove and again keep. Why? The same component, but one time you are not able to keep properly, but one time you are keeping the properly. Why? Because this, if that one is going into the hole exactly in the same line, then it will go freely. But if you are keeping like this and trying to move, it will not go. The rack also same. Right? There is an angular inside. So if the track moving exactly parallel to the hole, then it will go into the hole. But if it is moving in a different angle, it will not go into the hole. Am I right? Huh?
Yes.
So here in the dimensional tolerances, we are talking about only diameter and also tolerance on the dimension. Okay. But even though this is in the same limits of the dimension, but if you take the axis of this one and axis of this one, the two axes are not matching properly, right? And maybe if this is a hole, okay, suppose we have a component like this, and I want to keep some shaft into this. But if I keep the shaft like this, that is, the axis of this hole and the axis of this shaft is not matching, then it will not fit into that one. Am I right?
Yes.
So how can you ensure whether the shaft is exactly going or not? Because already the diameter of the hole you selected and dimensional tolerances also is selected, and this component also already you are given dimension and tolerance. So while manufacturing separately, both are qualifying for quality, but while going for assembly, there is a problem. Okay, that means then the concept of geometric dimensioning and tolerances are came into the picture. Okay, that means sometimes the only dimension is not sufficient. Along with the dimension, some other features, that is geometry, also important, right? that is normally that geometric dimensioning and tolerancing means that is a dimensioning and tolerancing a drawing which considers the function of the part and how this part functions with the related parts. Right? That is, for example, you are manufacturing separately this bottle and this one. Both are correct. But if the axis is not exactly matching, then you cannot fit it this one. So like this, this GD&T gives or eliminates that errors if you define properly. Okay, that is the main criteria. You can see one example. So we are making a table. So there are 4 legs. So I want the height of each leg is 27 centimeters, for example. So definitely we should give a tolerance because we cannot manufacture. So the tolerance given is plus or minus 1 centimeter. So while manufacturing all the 4 legs separately, if the dimension is 26 centimeter or 27 centimeter or 28 centimeter, I have to accept it, right? Because that is within the limits of the dimension. Then after making all the 4 legs and the top surface, then while assembly, if the legs are like this, different dimensions, 26, 27, 28, 26 legs, then what will happen? The top surface is not flat. That is what you feel sometimes in our house, the floor is not flat, or maybe sometimes whatever you are purchasing, birva or table or rack, it will be slightly moving, so we keep some papers or something else. Why? Same reason. Because all the legs are not having the same length, or your floor is not having the flat surface. Any one of the reason gives tilting in the component. So we have to avoid that one. Normally in our house, we use papers or some pads or etc. Depends on the weight of the component. So if you define other condition here, like this surface should have the deviation of only so and so, right? Go to this. So along with this height, I also define like this. That is, the deviation allowed on the flatness of the top surface is 0.06 mm. Or if you are following, this is centimeter, this is also centimeter or inch, whatever. Then what I can do, even though we are manufacturing the legs with the same dimension, but I cannot select the legs randomly. I can select the legs which are nearer to the same height, like whatever we discussed previously in a group, and I can see that this one already ensured while manufacturing a individual leg, but I have to ensure the flatness of the top surface. Are you understand? So you are keeping another constraint or another condition to ensure the quality of the product. So that is what actually we do in a GD and T. So if only this is given, this is normal dimensions. That is dimensional tolerances. But no geometry is involved in that one. But here the flatness criteria also involved. So that is why we call it as geometric dimensioning and the tolerances. Okay.
Flatness tolerance 0.06 you mentioned. So how to arrive 0.06?
That is what where another different tests are there. So for flatness measurement we have different
Suppose
tests.
0.2 is enough, 0.06 you mentioned. So this is
This is
based
what
on
I am
any
telling
chance.
example.
Yeah.
but you may take 0.02 also. That depends on the application, depends on the functionality, right? See, for example, if you take a chalk piece, right? That is a single component. And what is the length of the chalk piece? Approximately
7 centimeter.
6 to 7 centimeter or 6 centimeters, I can say. So, how can you decide the tolerance? Yeah. So, for example, this is the chalk piece, and the length is 7 centimeters. So, I can write 7 plus or minus 1. Okay. Why we are defining 7 centimeter? This is a single component. What is the functionality? Writing
On this blackboard.
smoothly or properly. It should be comfortable to the writer. So actually here the functionality depends on mostly on the quality of the powder what we are using, and also quality of the blackboard, but not on the length. Okay. Here length is for our convenience. So if it is too long, I cannot hold it properly, or if it is too short also, I cannot hold it properly. So the length is also important, but it is a secondary functionality. So even though if I give the tolerance plus or minus 1 centimeter, it doesn't affect the overall functionality of the component. But at the same time, if I take this my pen, right, and then you take this refill, this length of the refill also approximately 7 centimeter. Can I give tolerance to this one like 7 plus or minus 1 centimeter?
No.
Is it possible?
No, sir.
Maybe I can give 7 plus or minus 0.01 centimeter, or maybe 0.05 centimeter. That means the deviation allowed on the manufacturing of this length is very less, and the deviation allowed on the manufacturing of this chalk piece is very high. Why? Because this is the assembly, and also the functionality is different. That is a single component only for the writing, but here there is a action, there is a spring, there is a movement, everything. So here tight tolerances are required, but here tight tolerance is not required. Similarly, this one also, either you can give 0.02 or 0.04 or 0.06, that depends on your application, right? If the table you are using for rough use, it is okay. Otherwise, you want very precise. You are holding glass items, or you are holding some mobiles in a shop for display, etc. Then the deviation, much deviation is not allowed. Right? Just this is an example I am saying. This value we can decide depends on the application again, and depends on the material what we are using, and depends on the manufacturing process, etc. But here the importance is not on the numerical value. The importance is defining the flatness of the table. Okay, are you understand? So along with this dimensional tolerance, we are defining geometrical tolerance also. That is called as a GD&T. So with this one, we can able to improve the functionality of the components, and as well as the accuracy of the components, etc. So if you define like this, then the top surface of this one should be within that deviation, right? So that for that reason, either you have to select all the legs at 26 or 27 or 28. This is what already I told you in the grouping of the component. To achieve this one, we require grouping. Okay? that is just a length. That's why normally we are using the higher limit or lower limit, such type of condition. But all the components are not simple length and diameter or height. There are complex shapes also there. So that's why normally if this is a cylinder, right, then we can define an envelope. So the cylinder is also having errors on the diameter, but not only at one place throughout the length, right? So that's why we define this envelope, which is also a cylindrical shape. So this black color is the actual cylinder, and this red color is at higher limit, and this blue color is at a lower limit. So what we can do here, we define lower dimension, that is lower limit of the diameter, higher limit of the diameter, as well as we define the cylindricity error also. That means even though the diameter is varying, the total surface should be within that envelope, right? So then only we can able to achieve the functionality of this component. Like this, if you have any different shapes, then you need to understand that one. Okay. So you see the same cylinder, you have to keep inside this box or some rectangular or cubical part. We have a hole, and this is inserting. That is what I already told you. Maybe if you are not following GD and T, if you measure the diameter of the hole at this end or at that end, it is satisfied. And similarly, if you check the diameter of this cylinder at different points with the vernier calipers or anything, micrometer, it is also satisfying the dimension is between the lower limit and the higher limit. But however, sometimes you may not fix this one into this. Why? Because the axis of this one may not coincide with the axis of this. Okay, and here somewhere it is at lower limit. At the same point, this may be at higher limit. So that is why we have to define the cylindricity error also on this one, as well as we have to define the axis of this cylinder and the axis of this hole should be parallel. Like that, depends on the shape, size, and functionality, the more number of constraints or definitions we can add to avoid the inaccuracies and to increase the accuracy and precision of the component, right? So this is what the need or necessity of the GD&T. Okay. So like this, if you have the parallel lines, if you want to check the straightness of this surface, the straightness we can check between the two lines, and the parallelism we can check between the two parallel cylinders or parallel lines or planes, and this is also parallel lines. So here line is a straight line, here line is a cylinder, here line is a curve. But whatever may be the shape, the total envelope should be within that value, right? And similarly, if you take plane, this is the only lines. This is the planes. So if you take the flatness or cylindricity or some other plane, curved plane, so then this total plane should be on the top plane and between the lower plane. Got it? And similarly, sometimes the planes are like this also, the parallel planes, and here also parallel planes, and this is the cylindrical zone, right? So the center of the cylinder should be within that zone. Okay, I'll show you. So in the total GD and T, there are classifications. So that is the type of tolerances is called as one type. First type is form tolerance. Okay. So under form tolerance, we have flatness, straightness, circularity, and cylindricity. Like whatever we saw in the example table, right? Along with the height, we have to define the flatness, right? And similarly, we have to define sometimes the straightness. We have to define sometimes the cylindricity, and we have to sometimes define the circularity. Okay. So these are called as the form tolerances. Why? Because these are the individual features, right? Individual features. But these individual features sometimes may be a related features. These are called as profile features. That is line profile or surface profile. Okay. So flatness and profile. These are also individual profiles, but sometimes this is linked with the some other feature, right? For example, uh, we can say, like it is same thing. The outside diameter we can define, and here also inside diameter we can define. So if you take this, you forget about these threads and shape outs. So this outside diameter and inside diameter, if you are defining, then the inside diameter is always with respect to outside diameter, because we have to maintain the same thickness, right? Of course, thickness variation also allowed, but again we have to define what is the variation allowed. So like that, here sometimes flatness, straightness, circularity, cylindricity, or maybe line profile or surface profile. So all these are the individual features. Sometimes these two are related features. That means related to something else. Okay, but these features are there. These are orientation features, or runout feature, or location features. All these are not individual features. Okay, all these are exactly related features only. Individually we cannot define. That means we have to define all these features with respect to something else. Okay, with respect to something else. Suppose I want this roof, okay, should be horizontal. How can you say it is horizontal?
Measuring instrument.
See, I want this one flat, means you can say flat, especially also flat. Suppose you take any book or mouse pad or something like this, then this is flat surface. So if it is like this also flat, like this also flat, like this also flat, right? Are you clear? But at the same time, now I want this surface should be flat with respect to floor.
Parallel.
So this surface should be parallel to the ground. Similarly, this ceiling should be parallel to the floor.
Perpendicular to one.
So flatness also required, but with respect to this one. So like that, if we want this pillar should be perpendicular to the floor, right? So that means that perpendicularity we check with respect to this floor only, or it should be inclined at for example 80 degrees. I cannot say with respect to table, but it is in. I want inclination of 85 degrees, means
With respect to flow.
obviously by default we are defining with respect to this table. Like that, all these features require some reference. So that's why these are called as related features, and also the reference we can call it as a data.
So profile, line of the profile, sir. So how to link the individual or related? This is the profile one line only.
Right.
So suppose surface is okay. So suppose you related to other surfaces. So line of the profile, how to check it?
That is what I told you. For example, this one I want cylindrical.
Okay.
So cylindrical means you can check circularity and further length.
Right.
But at the same time, we can use some other one where we are keeping the another cylinder into that. This is outer shell, but inside we have some concrete cylinder. Then with respect to this inside concrete pillar, this outer shell should be same profile. Got my point? See, I will give you another example. Suppose you take this cover. Take this cover. So this is normally a flat. We can define this is, forget about these edges, all these things. This is a flat, right? So individually, if you see, this is a flat component. But when you want to assemble with this one, so this surface should exactly match with surface of the phone. Am I right?
Right.
This is a flat one, but like this, some curve is there. So this curve, with respect to the phone curve, should match. So that is why this profile, maybe you can define separately also, or sometimes depends on the application with respect to something else also. Got my point? But if you see these features, wherever you define, you cannot define with respect to other one. It is individual. But these two, sometimes individual, sometimes depends on the other things. That is why these we can call it as either individual or related features. But all these are the definitely related features. Without some reference, we cannot define this. That reference we can call it as a datum, right? So these are the normal symbols we can use: maximum material condition, minimum material condition or least material condition, and projected tolerance zone and all these things. Maybe you can know. You can see in the any of the softwares also. So like this, we can show all the geometric tolerances in a box. This is the exact standard indication of the things. We can call it as a feature control frame. So in the first box, we can define the geometrical symbol. That is what we saw previous. And then here we define the information related to tolerance. So on this geometry, how much tolerance is allowed. And here we define the datums. If you remember the first example, on the table, we are given only the symbol and value because that is the individual features. That is why these three are not there on that feature control frame. Only we are giving the geometry is flatness and the value allowed is some value. But if you are using the related features, then we have to use these boxes also, where we can define here primary datum, secondary datum, tertiary datum, like that. But not for always all the component. Sometimes only one datum is sufficient. Sometimes we require two. Sometimes we require three. Right? So like this, we can read this control scheme like this. That is the flatness of the feature must be within the 0.06 mm relative to datum A, datum B, datum C. Like that, we read this feature control scheme into a sentence. Okay. So like this, we can define. This is one example. So this indicates geometric symbol, that is position, right? And this indicates the numerical value. This indicates that numerical tolerance is at maximum material condition. and with respect to primary datum, secondary datum, and tertiary datum. That means this one we are defining all the three datums. Sometimes we require only one datum. Sometimes we require two datums. So that is what already the individual features without datum are this one, that is flatness, straightness, circularity, and cylindricity. The same thing, whatever there in table, just I am showing in the diagrams. Okay. Then next, that these features require datum features, that is perpendicularity, angularity, parallelism, and circular runout, or total runout, or radial runout, and position, concentricity, and symmetry. So normally here position means, for example, you take any of the component, we want some hole at the center or at somewhere else. Then how can you decide the position of the hole? We can say position, right? We use this word regularly. Suppose you want to keep your sofa in your house, you can select a position, right? But are you exactly keeping at the required position, or you are making a hole? Are you exactly making the required the center of the hole matching with your exact dimension? May or may not, right? That is why we follow this. We define this position and then concentricity and symmetry. So this is the one we define. This is also another example. So here this is datum A, this is datum B, right? And this surface we are defining with respect to datum A. That means this surface should be parallel to this surface, and this surface should be inclined to this surface. That's why we are writing here B, and here we are writing as a A.
Sometimes some drawings are right side of the right side view. So datum A is mentioned for right side view, datum A.
Pardon?
Datum A is mentioned, datum A, this is surface. Some right side view is fixing, datum A. Primary datums.
You mean?
Datum A, right side view, is fixed for datum A. Some of the drawings, most of the drawings. This is correct or not?
No. You are asking only we fix right side view.
Right side view, datum A is fixing.
That is what I am coming there. Just wait a minute. So this is an example of showing the datum A, datum B, or datum C like that. So we can use different datums with either A, B, C letters, etc. Next. Right. You can see this. So this is the datum A, right? So, for example, you are keeping this table, and I want the table flat. Okay. So here I need one datum, that is the floor. That is sufficient because I want the table should be flat. Okay. But at the same time, I want to keep this table flat and also perpendicular to some other wall. Then I can use the secondary datum, or sometimes we use that corner, right? So that one should be perpendicular to that wall, this wall, whereas parallel to the bottom. Then we use three datums. So normally, I think you are all studied the 3-to-1 principle in the jigs and fixer designs. So once you are fixing one datum, normally 3 degrees of freedom will be arrested, right? Then you are fixing another datum, then 2 degrees of freedom will be arrested. Like that, which one or which surface is giving more visibility to your component, that one we select as a datum A. So whatever you ask, always this may not be datum A. Sometimes this may be datum A, depends on your component, depends on your manufacturing process, or depends on your size of the component and shape of the component, or maybe depends on the machining process what we are using. See, for example, you are making a rectangular component, then the datum may be a bottom surface. But not like that. You take maybe a chess coins. These are having so many curves and symmetrical. So in that case, the datum may be different. The axis may be another datum, like that. Okay. So like that, depends on the component. You have to check which plane can able to give or define more features on the component. That is the datum. That is the primary datum. And then if one datum is sufficient for us, only we stop with primary datum. Suppose you are not able to define all the features with one datum, then you have to search for secondary datum. If required, then you have to go for the tertiary datum, right? Next one. So this is called as a size datum. That means the datum may not be always a plain flat surface. Sometimes the datum may be a circular surface also. Inside a hole, the inside surface of the hole may be a datum, or sometimes the outside surface of this shaft may be a datum, or sometimes some other plane may be a datum. We don't know, because if you see, in this case, the outer side, this component, the cylindrical component is going into this one. So now this outer surface of the hole is the datum. With respect to that datum, the shaft diameter should be parallel, or the axis of the shaft should be parallel, like that. Okay. So like this, we can define datums, and we can use the GD and T to get the more accuracy and more functionality exactly to the whatever we require. So sometimes without knowing also in the software we use dimensions, we use these symbols, surface roughness symbols, etc., etc. But if you understand this one, then it is very easy to use, and you can able to make the better assemblies. Okay. Go back to original. Okay. So this is one example. Okay. So this is the component, right? So this is the top view, or you can say parent view, whatever it may be. And then this is the side view. So here, this is circular part. This is also circular part having some thickness. Now the condition is, if you see from the top, this is the part, this one, and this is the part, this one, and again we have a slot here. So if you just see this one, the bottom surface we can keep on the table or something. So this may be a one datum, and this surface should be parallel to this surface, and this surface should be parallel to this surface, and again the hole should be perpendicular to this surface, and again this slot. So this slot should be again maybe perpendicular to this one. That means this surface, this line should be perpendicular to the bottom surface. Like that, there are so many conditions. So we can show like this. This is the datum A, right? So where we are defining this one, and the whole, right? And we can define number of datums, that is the perpendicularity and position of the hole, this hole and this hole and these holes, and position of the slot, and then this should be perpendicular to something else. Like that, we define each and everything so that we try to eliminate the errors in the manufacturing process. Suppose you are not saying this surface or this surface should be parallel to this surface, then what will happen? Maybe dimensions are within the limits. This separately, if you measure this dimension, correct. Separately, you measure this dimension, correct. But this surface cannot be parallel. Okay. In that case, what will happen? If you are keeping some shaft into this hole, that will not match, right? Or if you are fixing some bolts or some other part, then it will not match, right? So in that way, actually GD&T will improve the quality of manufacturing and the functionality of the products, etc. These are all just small example or basic, but there are so many things in the GD&T. You have to learn to improve your the maybe your simulation or drawings, etc. Whatever. If you want to do without any errors, you should understand these things. Okay. So I think I took a lot of time. I can complete with this one. So if you have any doubts, please ask me.
Thank you, sir, for your insightful lecture. So thanks for all the audience for your patience listening. It was almost 1.5 hours. So and you are with the same enthusiasm what we started with. And I would like to thank sir also for his patience and out of his health condition and all, he has given a big lecture for all of us. Today's GD&T is very much useful. So who are preparing for interviews and all, please take it. Who are preparing for this GATE exam and all, this content is very much useful. So this is available in our YouTube channel. You can please like, share and subscribe. And you can also follow our coming up sessions. And with this note, I would like to tell one thing. So for arranging this session, Sir has to travel almost 120 kilometers more than his usual journey. Actually, he booked the tickets for today evening from Chennai more to Warangal, where he can directly step down in in Kazipet Junction, and just 10-minute walk, he will reach his house. But out of my repeated things, because in our recent data collection, maybe I will not take too much of the time. So in our recent data collection, we identified that almost 49% of our staff are graduates. Another 35% are PG holders. 14% are PhD holders. Don't calculate all these to become 100 because I am giving a nearby values. Okay. So what I thought is arranging this kind of sessions will definitely help you in achieving good ranks in GATE examination. Okay. Maybe some of you, I know you are appearing for GATE, and it will be an enlightening session. Particularly in GD&T, we don't have regular curriculum courses, if I am not wrong. So only those people who are into industry are more into GD&T. So Sir has got 19 years of experience in the same subject. Maybe you might have seen this. So I wish you can interact with him for another couple of minutes, and he will definitely answer you. Maybe not on this session. You can ask on this session, or your for example, you want to register some PhD or some kind of future aspects. You can interact with him, and you can learn some good things from him. Another 5 minutes is possible for us. Then we will go to quick facilitation of sir. Then we will have a vote thanks, and then we will disperse. Okay. So now the session is open to you. So I request at least 4 or 5 questions from our enthusiastic audience. So please go ahead. So you can come here, share your feedback. So all our spoke center people are watching. They will also, see, and next time they will also participate. And it will be an encouragement for us to arrange this kind of sessions. Maybe next time we will plan for CFD or some other kind of simulation topic. So one we have seen in design. So one we will see in simulation. One we will see in digital manufacturing. Okay, we will try to see. I don't say it is 100% possible, but I will try my best along with my team. So now the session is open for you. So I don't want to take much of your time. I want 1 or 2 to come forward and share your views, and you can ask sir anything sitting there also. Please. Of course, Satish sir asked a number of questions. Sir, he is our business development manager. So he will go for many interviews and all. So that's why
already is working Canterbury. I know.
He has 10 to 12 years experience in GD&T. So anyone? Or may I wind up the session? It's up to you. No need to fear and all. Feel free because this kind of chances we don't get often. Okay, getting sir from Warangal, talking to him is not that easy. Make use of it. Okay, then that's fine. I don't want to trouble you much. So, quickly completing. So, I would like to welcome our center head, O. Mililan sir, to come forward. Yeah. Please.
I want to know about.
No, not to me.
Sir, I just
Please.
I just want to know about the GDNT tool. One of the GDNT tool is used in industries. So, what the profile of the surface? They have been mentioned in so many drawings. The profile of surface. So the GDNT. What is the purpose of GDNT to use on the drawing?
Yeah, that is what I am saying. Purpose means always you're talking about profile, right?
Yeah, profile of surface.
Surface.
Yeah, that is what the profile of the surface they are indicating means that profile is very important for functionality. And again, either that profile may be a individual feature or related feature. Suppose maybe in the drawing you can see as an individual component, but when it comes to functionality, it is going to the assembly. This profile may be matching with some other profile, so that both the profile should have the same thing. That is, for example, I'll show you.
Piece for any piece for drawing should be done. So any
Yeah, sometimes we can have different components, right? I'll show you. Have you seen ACs are there? Inside ACs we have a filters.
Yes.
So I think we have to oftenly clean the filters. So do you observe that the profile? I mean shape of the filter? It is like this.
Yes. Right.
So it may be if you open, it may be slightly bending, right? But when it goes inside this, it is like this. So to go this filter inside at the edges, you have a slots.
Yes.
So the profile of the slot is a curve, right? And this filter edge also a plastic or fiber, which should have the same profile. Then only this filter is going into that one smoothly, right? So in that case, this is not individual feature. This is related feature. Are you clear?
Yeah.
But sometimes when we are using some chalk piece or some bottle or
I
something,
have seen in one of the forging drawing.
okay,
They have mentioned that forging surface they have need a profile of surface about some other. They have mentioned it on that drawing.
that is what I'm saying. The component drawing maybe they are given, but if you understand the functionality of that component, if it is going to the assembly or the assembly is going to the functionality, then only we can understand whether it is individual feature or related feature. For example, you take this curvature. This is the individual feature. This is just for holding purpose. So even though this profile is slightly deviated, it doesn't much effect. But as I told you, the AC filter profile is deviating or the slot curve is deviating, the filter will not go smoothly. You have to apply a pressure. Sometimes it will break or like that. So these are the things we can observe in the so many are there. Maybe if you take your remote, right, backside you want to change the batteries, there is a cap. Right? So it's simple. You take this one.
Yes.
You take this one. So here we can keep like this and we can press it. So if you take this pin or this one or this profile should match exactly with this hole. Otherwise, when you are keeping like this, you have to apply more pressure or less pressure, or maybe after few uses, it will break.
Yeah.
You got my point?
Yeah.
So when it going to the assembly, it is linked with the other surface. If it is not like that, just a bottle, we require circularity, but it is an individual feature. Is it clear?
Yeah.
So any other? Yeah, please.
Sir, I had one doubt, sir. In a mass production, is it able to produce multiple components but the same size using CNC or VMC or advanced manufacturing process, sir?
Okay.
Is it possible or not, sir? Rather than comparing with traditional manufacturing, sir.
See, rather than conventional machining in CNC, maybe you are getting more accuracy, but not 100%.
Okay, sir.
Right? Why? Because here the operator is checking the dimension or maybe changing the speeds or speeds. So slight variation is there. In the CNC, you may get more accuracy, but still it is not 100%.
Okay, sir.
Right? But at the same time, see, always accuracy is not important. Sometimes cost also important. Am I right?
Yes.
So always you cannot go for CNC machine. Always you cannot use high-end machines. So if you understand the concept, then whatever you require, that only you can opt. Right?
Thank you, sir.
Okay, then fine. So I invite our center head Eril sir to presentate our guest. Sir, please. Sir, please, you also join. So, Dr. So, focus. So, coming to the end of the session, so let me give the vote of thanks speech. As we come to the close of this enriching session, it is my privilege to deliver the vote of thanks on behalf of TANCAM. So I once again thank from the bottom of my heart, from the management side and from all our sides to Dr. P. Vamsi Krishna sir for taking immense, taking a lot of pain and things to come here and deliver a lecture to us. So I would like to extend our deepest gratitude to Dr. P. Vamsi Krishna sir, professor at NIT Warangal, for sharing the valuable insights on precision manufacturing. So your deep expertise, clear articulation, and inspiring research journey has truly enlightened us. We are honored to have had the opportunity to learn from you today. So I would like to thank sincerely our mentor, Mr. Sauri Rajan sir. Of course, his sir is not in the event; he is in an important meeting with Health Minister. So for being part of this event, even for the shortest of the time, and his presence and constant encouragement and strategic leadership that enables us to host such meaningful sessions. Along with this, I would like to thank our COO sir, Mr. Vijay Deepan sir, from the bottom of my heart, without whose encouragement and whose permission this event would not have taken place. I extend my warm thanks to our center head, Mr. O. Melilan sir, for his seamless contribution and ongoing support to make events like this possible. So, sir always gives a positive hand to all of us whenever we come with a new thing. Sir and Saranam sir will come forward and always help us in making this kind of events happen. Because see, in our daily activities, we are always in a busy schedule. In spite of this, making you sit for a while, taking a lot of initiatives like this, we would like to thank our center heads sir, also our Deepan sir, as well as our Sauri sir. So please give them a big round of applause. So I heartful thanks to our technical manager and our senior research manager, Dr. Sivaram Krishnan sir, whose technical direction is the backbone of our operations and whose presence today reinforces our commitment to innovation. So when we bring this kind of concepts in our meeting, sir is always in the forefront, encouraging us, telling you do like this, you do like that, this is not good, this is right. So because I am also a junior like you, so I learn many things from them. And to all our colleagues, team members and attendees, Thank you for your active participation and enthusiastic engagement, for your lot of patience for listening to the lecture, and your curiosity and presence makes these events truly successful. So last but not the least, my sincere thanks to everyone who worked behind the scenes, Patrick, Blessy, and other people who has Bhardi, who has Mr. Alvin, I need to mention. So you can clap for them. So they have taken a lot of time in gathering all the necessary things to make this event and a nice organized one. So from logistics to communications for making today's session smooth and impactful. So with this, let us carry forward the knowledge we gained today and continue to build a culture of continuous learning and technical excellence. So thank you and have a wonderful evening ahead. Okay, so thank you very much. So one last word. So I have learned many things in spite of if I say so many things, you will be feeling like Sir is his guide, so he is praising him. It's not like that. So I learned many things from him in person. So he is the one who guided me when I am in really hardships. Doing PhD for 5 years, it's not a simple thing. So he guided me continuously throughout the journey. He is like a wall to me. Whenever I am in a setback, I used to go to him, sir, this is my personal problem, this is my technical problem, this is my professional problem. Any problem, he's always in the forefront to help me in solving such issues. So I take this opportunity to thank my guide, my mentor, and my inspirer, Dr. Vamsi Krishna, sir. And thanks for considering my request as well to come here and take it. Thank you very much. So you can leave. Thanks for it. Thanks very much. Close the session. Sir, good evening, sir.